Thank you so much. Thank you for the organizers for the kind invitation. And I apologize, this is going to be in English, but at some point I need to learn Spanish, right? So I'm going to be talking about just kind of broad considerations in designing an imaging AI project. I think based on the lectures I've participated in today, everybody has a lot of expertise in some parts of AI project design. From an MD perspective, I wanted to kind of share what things might be helpful for somebody that's new, relatively new to doing AI imaging. And so just some brief disclosures, nothing relevant to the talk. So when you're designing an AI project, usually it stems from an idea, right? In that you have some sort of an idea about doing some kind of project. The problem with ideas is that not all ideas are equal. Some ideas are obviously a little bit better than others. And some of it has to do with the type of idea that is being generated. Meaning, sometimes you have a hammer, and then you kind of think of, okay, I have a tool over here, and let me try to figure out what I can do with this tool. And unfortunately, I guess a lot of AI projects started out like this. Maybe now things have changed a little bit, but a lot of people initially were interested in AI as a tool and then tried to find projects where they could incorporate AI into that project design. And honestly, it doesn't work too well if you do this. The second potential is if you have data, and this still goes on to this day. I get a lot of emails from people that say, "Hey, I have all of this data, and I don't know what to do with it. Can we do an AI project related to this?" This is better than just saying, "Okay, I'm interested in AI, and then I want to do something related to AI," but still not optimal. And the best course of action really is if you have a problem that you need to solve, right? And then you want to use AI to solve that problem. And the thing with this is that sometimes AI is really not the tool that is the best for solving that problem. But at least if you go from the question of, okay, I have this problem and how do I need to solve it? And then AI could be a part of it, then that makes more sense. So when you then combine, obviously, you need to have the data. But let's say you have a problem and you might need to solve that problem. You need to make sure you have that data for that as well. So that becomes a secondary important thing, right? And each institution, for example, has areas of expertise. At Hopkins, for example, if somebody asks me, like, I'm interested in AI and then I want to work on a project related to tuberculosis, then I would say, okay, that sounds interesting, but the problem is we don't have data pertaining to that. So that might not be the best project to work on. As opposed to cases where we have tons of data. For example, we have a huge multiple sclerosis center. So this obviously makes sense to everybody, where you want to have the problem saying that, okay, we have a large cohort of multiple sclerosis patients, something that people have already done, for example, or like, okay, can we do MS lesion segmentation, right? Because we don't want to have the radiologist spend too much time interpreting images. That sounds a good, okay, project that has a problem. And then we have the data for doing that. And so that sounds like a good problem to tackle. And so once you kind of think about that project to tackle, really the question is not how you start the project and go from start to finish. I think that's probably not a good way to start this, but to envision what the final product would look like, meaning what is the output that you want to generate from your project, and then work backwards. Because just based on experience, the problem is if you start from the beginning and then try to build upon that, then it shifts quite a bit. And I'll talk about this a little bit later as well. So a lot of this talk actually is based on a paper that I find really, really helpful for people that are starting out with projects called Deep Learning Workflow in Radiology, a primer. And then this has a really nice checklist, which I'll show you later as well, that you can go through if you're interested in doing an imaging related project. So for typical imaging related projects, really the scope in the beginning is going to be, again, at the very end, you're going to think about what output you want, but it could manifest as different types of projects, right? Is it going to be a processing reconstruction type process? Is it a quality enhancement project? Is it a segmentation project? Is it a classification project or monitoring project? And the tools that you're going to use are going to be dependent upon, again, the output that you're interested in. So just going through the important elements of I think, a good project. I'm going to run through the 6 or 7 elements here first, and then go into them in a little bit more detail. Number 1 is personnel, the people that are involved in it. Number 2 is to make sure you're cognizant of regulatory issues. Number 3 is the data, like we talked about a little bit. Number 4 is the infrastructure that's available for the project. Number 5 is the model that you're going to use for the project or software. And then number 6 is going to end up being the deployment once you've essentially finalized your project, right? And one caveat is that the process of this, which was actually mentioned in the previous talk as well, is not actually linear, meaning that it rarely happens that you have the people, then you work through your regulatory issues, right? With the IRB, that kind of stuff. You get your data, you figure out your infrastructure, your computational needs, you develop a model, and then you have a good model, and then you deploy. I feel like that never, ever, ever happens. I don't know if somebody's successful doing that, let me know, because I need some hints as to how that works. But typically, what happens is that you go from one, and then, at the infrastructure, at the point of looking at the infrastructure, you realize, oh, wait a minute, for the data that we have, I can't use the infrastructure that we have. And so we got to go back to the data. Maybe you don't have the computational resources for the amount of data that you need. Well, now you have to go back to the data and maybe tone it down a little bit, maybe change the project outlook a little bit. Well, once you figured out the infrastructure, then you go to the model design stage. And then again, if you're doing this from scratch, you might realize that, well, as we're building the model, we realize that the data is not as homogeneous as we wanted, or there's some outliers that are going to create problems. You go back to your infrastructure, back to your model, back to the data, et cetera, et cetera. And then once you finally got the data cleaned up, which is a very important part of the study, then even iterating the model obviously takes quite a bit of time, right? Over and over again. And once you're happy with something, then eventually you get to the deployment stage. So just, I think many people who've already worked on projects are very, very aware of this, but AI model development or project is not really, to me, a linear process, even though it's supposed to be a linear process. And so this is kind of like a circular example. Even when you have the best of intentions, so once you collect the data, you explore your models, you refine your models, that is an iterative process. And then monitoring, maintaining the algorithm, right? And to make sure that that is still suitable to ongoing data interpretation. That's also an important part of AI research and even implementation. And as mentioned, Dr. Castano had mentioned this before, the project lifecycle, which essentially says the same thing, that there's different steps in AI project development. And I wanted to add that again, that it's a very, very iterative project. Iterative process. So going through each one of these, the project manager, the clinical expert, technical expert, worker bee, these are the 4 categories of individuals that I feel like I've identified that really should be present. Now, the thing is, sometimes people can do 2 different things or 3 different things. It's very, very rare for somebody to be able to do everything, meaning that you can be a good project manager, organize everything. You have the clinical expertise in imaging. You also have the technical expertise in programming, and you can do all the annotations, for example, that you have the time to do that. Very, very rare, right? But then sometimes, the clinical expert might end up being a good project manager. Maybe the technical expert might end up being a project manager. So in my lab, between myself, who I'm a clinical expert, I sometimes as a project manager for some projects, but I also have a PhD that I've been working with for a long period of time. And some projects he is leading, and then I'm supporting with the clinical expertise. And separately, I feel like the worker bee is someone that usually has a lot more time for annotations. Annotations, I think, is a very, very expensive and time-consuming part of AI projects, especially if you need a lot of data, right? And then so there's a lot of techniques to kind of go around this a little bit. And then nowadays, there's newer techniques like, zero-shot or few-shot learning that might be helpful in the future. But to date, most of the people are working on highly annotated projects, data with a lot of annotation. So this is, again, maybe the relationship between the project manager, and then you have clinical expertise, usually the physicians, and then the scope of what they do, right? In that they are usually looking at the formulation of the problem. There's the imaging expertise, which to me is going to be the same as clinical expertise, looking for the imaging, making sure the quality control is okay, looking at lesions, overseeing the annotations, for example, that kind of stuff. And then the technical expert that are looking at the data set and developing the models. In terms of regulatory issues, I think all institutions have an internal review board for doing research projects. And at Hopkins, we have an entity called the Data Trust, which incorporates a lot of these people, which is interesting because when we first started doing things like 4 or 5 years ago, Data Trust didn't really bother us too much. And mostly it was just kind of getting through the IRB. And they were looking at our little machine learning projects as, okay, you're playing with little toys and then don't worry about it too much. It's fine if you ask for a lot of data and then just let us know how things go, right? But then people started talking about big data. And then the IRB started freaking out saying, oh man, there's a lot of data that people need. And what if there's people hack into our system, which has happened multiple times, not only at Hopkins, but many, many institutions, right? So how do you keep the data secure? Who's going to have access to the data? Where's the data going to be kept? How to anonymize the data? These are all questions that the IRB and the Data Trust are now asking. And the question of anonymity also is a complicated question, right? Because before, it used to be that, at least for imaging projects, and we do typically MRI or even X-ray is fine, but you just have to get rid of the DICOM information that's attached, the metadata that's attached to the images. But the problem is if you're working on head imaging data, then you're going to have to get rid of nowadays facial deblurring, because you can identify people from reconstructing MRI images of the face or even CT images of the face. Going into the future, the problem is that may not be enough either, because if you do brain extraction, which is one of the current solutions to defacing, if you do brain extraction and just get images of the brain, the problem is that there's probably enough unique elements in just structural imaging, but definitely functional imaging of the brain, that you can identify individuals from brain imaging data itself without anything in the face. So to me, this has been a discussion with the Data Trust and IRB saying that anonymization is not black and white. It's not whether it's anonymized or not, but it's an agreement on how much anonymity is sufficient for the project at hand, because nothing truly, I think, can be anonymized fully to the full extent. So then when you look at the data, two big questions that you want to ask: are you going to work on own data or public data? And obviously public data is a lot easier to work with. And there's a lot of repositories, at least for brain imaging, like the BioData, ADNI, OASIS, Cancer Imaging Archive, et cetera, et cetera. I think a lot of people go to Kaggle to look for data as well. And then there's competitions that you can also look at, right? For example, the Radiology Society of North America, or the American Society of Functional Neuroradiology, and the American Society of Neuroradiology. They come out with like challenges, imaging AI challenges, and then they put out annotated brain imaging data for people to work on imaging projects on. And those are good sources of data because they're annotated by experts. They're relatively clean data, although that's a whole nother topic of how clean it exactly is. And then we're actually trying to figure out some tools to figure out how much of the data is correctly labeled, because oftentimes it's not. And there are some tools that you can use, like CleanLab is one that's available, I think, as open source, to find out how much of your data is incorrectly labeled. And it works okay for some instances. If you're using your own data, then the problem becomes a lot more complicated, because then you have to figure out where the data is, how you're going to get it, where you're going to keep it, who's going to investigate the data and to make sure it's all clean, quality control, right? And then who's going to label the data, what's going to be the reference standard for the data. So all of these can take a lot of time. Collecting of the data is a huge issue, right? Because if you retrospectively collect data and let's say you need like thousands of data sets, then it takes forever to go back and do this. And if you ask a radiologist to do this, then unfortunately our time is super expensive. And just like a little anecdote here is that I had a company from Japan who was interested in validating AI tool that they had for measuring, detecting intracranial aneurysms. So they were approved in Japan. They wanted to get FDA approval in the US. So they reached out to us saying, hey, we just need, a couple hundred data sets to validate the data. Now, when we actually calculated what they needed to do just for several hundred data sets for validating their algorithm, it turns out that it was way too expensive for them to proceed with it. It ended up being like, unfortunately, close to $500,000, which sounds ridiculous, but they wanted a radiologist to be doing all of this. And that's how much it costs. So they ended up not proceeding with this. So there are tools that you could use to kind of prospectively collect data. So we're using a tool at Hopkins where, as we are reading cases, if we know that there's a certain AI project that we're doing, and we find a data set that is applicable to that project, and let's say it's like a head bleed detection. Now, there's plenty of head bleed algorithms already, so no point in doing this anymore. But let's say it was a head bleed algorithm. Then every time I see a head bleed, then I would just click on these two buttons, and then the data will be sent to a server and then collected. And then in the background scene, there's actually an active learning process going on, which is a separate story, but AI development is going on concurrently. Sharing of the data, let's say, so you don't have as much data at your own institution, so you can start looking at multi-institutional collaborations. Now, this gets complicated again from IRB perspective, right? Is anonymization especially, and then data security. So one alternative is to do something like federated learning. And here's a project that we were involved in, and a lot of institutions were involved in, and you can see by the author list that it was a huge effort. But just demonstrating that you can do federated learning. So this is essentially taking your own data and then doing algorithm development or training the model, let's say, at your own institution. And a central institution then would not require movement of the data, but they just need the algorithm that you trained. And then they would combine the algorithms centrally and then come up with an aggregate algorithm. So that would be federated learning. The part of the issue with this, some issues with this specifically, is that you really have to agree on the model beforehand, right? And then once you committed to it, it's very hard to change it because there's so many places involved. And then if you do change it, then you have to kind of redo things over and over again. And the other problem is that if you have few or one institution available, few is still okay. But let's say that you want to try to do this with one other institution. You can actually reconstruct the data based on the weights from the provided model. So if you, let's say Hopkins and the Italian hospital work on a project together, and then you are doing the federation, and we are supplying the models, it turns out that you can actually reconstruct the data from Hopkins just based on the weights, because you know that it only came from one source. So that could be a problem, just FYI. And so for infrastructure, the question is like, you can use small things like laptops or even like Raspberry Pis all the way up to like cloud clusters and things like that. And the choice really depends on the scope of the project. What we typically do is we have our students or the postdocs or the PhDs work on their laptop initially for prototyping, just to make sure that the data it is not giving you errors, right? If you need like 1,000 data sets, you don't need to work on all 1,000 at once. Just do one or two in the beginning and make sure that the algorithm proceeds without giving you any kind of funny errors. And then you can spend money on other resources, like if you have a workstation, single or multiple GPUs. In our case, again, we have a workstation with single GPU, but if we need more than that, then we go up to an institutional cluster at Hopkins. If we need more than that, then there's a multi-institutional cluster in the Maryland area where Johns Hopkins and University of Maryland have a collaboration. And if we need more than that, then we essentially go to the cloud. So from the initial prototyping, as long as we don't get errors, then we will move up to the appropriate level of infrastructure. And sometimes it happens that we think that it'll be okay using a workstation or cluster in the hospital, but we needed actually more compute capabilities. So you would end up eventually going to the cloud anyway. Model development. So before you do anything intelligent with AI, try to do things much more simpler. Honestly, like sometimes just simple machine learning, linear regression is sufficient. Let's not complicate things, right? But if you feel like AI is beneficial, then yes, do that. And two biggest categories of model development. One is to use commercial or vendor AI tools and then figure out like what's the validity of utilizing that tool and the performance of it. Or you could do DIY development, which a lot of you are doing. And we're not going to go into the different software available or the networks available, but you want to make sure that as you're designing a project, you know what output you want, right? If you're looking at classification, then you want your ROC curve to be your metric. If you're looking at segmentation, then you want your dice score, for example, to be your metric. So make sure your output, the end result, is appropriate to what you're looking for. And I think you all know this, so I'll skip this quickly, but you want to make sure that you have enough data for training, validation, and testing. I think commonly a lot of people are doing K-fold. Man, I'm blanking on the word over here, but testing, right? There's some statistical issues with that, even when you have a decent amount of data. So ideally, it's better to have test data that's separate. But I understand sometimes it's necessary to do other methods, utilize other methods. And then for deployment, you have to consider, okay, how are you going to distribute? If you're using your own data, how are you going to distribute it? What platform is it going to be distributed in? Because especially for clinicians, if you have an AI tool, but it's not incorporated into the workflow, then they're never going to use it, right? If you have to spend like a couple extra minutes to open up another software and then use a web-based output and then view it and then incorporate that into your interpretation, then that's probably just going to add more time than us just looking at it directly. So you have to make sure that it's seamlessly integrated. Clinical validation and then deployment and practice, which is kind of what I'm talking about right now, and then continuous quality assurance, right? Because as more data comes in, and sometimes there's some data shift, and then the model then becomes not suitable for the data shift that's occurring. Let's say that, I don't know, like the temperature changes and so your MRI starts drifting in some signal, or just because it's old, the signal drifts. And so there's this concept of catastrophic forgetting, that if you don't update your model with old data, then sometimes the algorithm that you use is not really suitable for ongoing use. And then there's a question of commercialization, which is a whole nother topic in and of itself. So as I mentioned, all of these things, or most of these things, I think are very, very well delineated in this article. And then if you are starting a project, I feel like this is super helpful to just kind of go through these checklists, right? To make sure that you've addressed all these issues before you start, and have the end goal in mind again, and then build up to that end goal. Just in the last couple minutes, I wanted to share some mistakes that we made in the several years of AI research that we've been doing. One is to work on projects that had no clinical impact. Again, this goes back to the hammer and the nail question, but initially we were all just excited about AI, and then, oh yeah, I know, so cool, we can detect these things with AI, and nobody was going to end up using it for actual clinical use anyway, right? So at this point, that's not sufficient. And I think even just to get published, you have to demonstrate that there's some kind of clinical impact. And this is kind of how our lab actually started, the radiology AI lab, because we got inquiries from the engineering group with repeated emails from tons of clinicians saying, hey, I have all this information, data, and I want to do an AI project. I want to look at this, can you help us with that? And they were offering services for free, but they didn't know which project to work on. So they reached out to us because we at least had some experience with some machine learning, and we were able to guide them on which projects would be important clinically. Doing it all yourself is not a good idea. Too much stress, you're going to lose hair. So try to make sure that you can delegate things, right? Not allocating enough resources. If you need compute infrastructure and if you need money for that, I mean, figure that out beforehand, right? And then not too late, and then finding out that, oh, well, I have all this data, we worked on all this stuff, but then we don't have either the infrastructure to work on or a medical student to do the annotations, et cetera, et cetera. This is a big one, is that, again, which is why I'm harping on the end result, is that even with a clear end result, the problem is sometimes the objective shifts. And that's okay to a certain extent, but it becomes a huge problem if you don't have that end result from the beginning. And then as you're doing your AI project, you start shifting your goals, and then you essentially never, ever get to finish the project. Overestimating available data was a huge issue. Initially, we had a bunch of projects. We even applied for grants, and then we said, yeah, we have like 500 data sets of these specific instances. And then when we actually looked at the data, it turns out we had like half of that, which became a problem. So I never trust anybody telling me how much data they have until they actually show me the data. And then how much time it takes to do data collection, curation, and annotation, which you probably know. Overestimating talent, students that say, yeah, I know how to do machine learning. I've worked with TensorFlow. And then when you ask them to do something, it turns out they had no idea, which, you just have to make sure that you can do some homework before that to make sure they know what to do. And then finally, too many cooks, meaning there's too many people involved in the project that doesn't have a project lead. And this is why one person is important, to make sure that the project lead is leading the project and deciding on important changes. That's it. Thank you for your time.